So, welcome to today's lecture, and as from we will continue with what we have done on the last class. So, today is a practical lab based session in which we would be doing a coding exercise. So, if you have followed down the last 4 lectures which we have finished off, so the earlier lecture was on actually getting you introduced to very linear perceptron model, and that's one of the most simplest model of what is called as a neural network and one of the foundational ones. So, today what we are going to do is basically a code implementation of a perceptron to be used as a classification model using the features which we had extracted in the earlier classes. So, if you remember from the third lecture, which was basically a coding exercise, and there we had implemented one particular code to extract out features of different kinds, and these included LBPs, Gabor wavelets, co-occurrence matrices, and a summary of those features which we had extracted from the complete training set as well as on the test set of CFAR, and then that was also stored down as a pickle file, which is your local file used within Python in order to store down your recorded matrices. Now, today what we are going to do is build up on top of that. So, in the last class I had concluded on the point where all of those files were saved and kept down for your offline usage, so that every time you do not have to reload your images and keep on calculating. So, today I will be taking up from that point onwards, where you have all the files which are saved down, and then appropriately from those I am going to take it forward and create a new perceptron model and use these features which were already stored in a pickle file by loading it from the pickle file, and subsequently go down to run a classification. So, the location is still the same. So, you will have to get it down from the GitHub link where we have been keeping all our codes posted, and then if you invoke the IPython notebook over there, so you would be getting down your lecture 5, which is your classification with perceptron model. So, it's lecture 5.ipynb, and that's the file with which we start. So, the initial part of the same file is the same header which is over there, with an extra point over there. I am also going to use this extra library called as time, and this is just so it does not have a major impact as such on your training in any way, but this plays a role in order to show you as to that we are accelerating using GPUs and how much time it takes down in order to get the computation done for every epoch. So, it's just to show you how much of is the time difference over there. Now, we have these parts of the header already preserved, and although they are not actually required, but the reason we preserved it, if you would like to have all the earlier computation also pasted along with this part of the code, which is you want to calculate the features, and once you have calculated out the features you would go into it, then this header actually serves as a very generic header to keep down and import all the functions which you need. Although this particular one on scikit's feature, that is definitely not something which is needed, as well as you will no more be requiring direct access to the torch vision data set, because all the required information have been stored down in your pickle file itself. So, these are optionals, but always a good guide to keep them keep going on. Now, in the last class what we had done was we had trained them and we had stored them into different pickle files. So, these file names may be different from varying to varying, but what you need to keep in mind is that you have one pickle file which is stored down with your features from the training data. There is another pickle file which stores down all the labels from your training data, and then we need to load basically these 2 pickle files. So, just remember your location and the file name which you have created. As such, if I am not giving down a very explicit location, this means that all these files reside in the same directory structure where my base code for running this one is residing. So, wherever your main code is there, it needs to be over there. Otherwise, if you are from some other location, then you can just append down the extra directory location from where these files are to be picked up. Now, once you have opened it up, the next part is to load this one. So, this is where you just define a file pointer as f, and then you use that file pointer in order to load your pickle, and you get your basically your arrays of training features and train labels. Similarly, you get your test set features and your test set labels which come down over here, and then like once this is done, there is interactive command to just display whether your matrices have been fetched down. So, let us keep on running one by one. So, this is the first module which has to be executed. So, once that is done, so it works out, you get your first instance which has been executed over there. Now, we go from the comment on to the next one, which is about loading. So, it shows that the feature matrices which were saved on the disk, they have been loaded. Good. So we can go down to the next one, which is to define my network architecture. Okay. So within my network architecture, how it goes down is, if you remember from our simple neural network, so what we had was, you have a set of inputs and you are just connecting it to an output, which is your classification. Now for classification over here, we are doing a 10 class classification. So it means that there are 10 neurons on which the output will be coming down, and these are a one hot neuron kind of a thing. So what that technically means is that whichever class is present, that particular neuron will be 1, everything else is going to have a 0 value over there. Ideally, that's what is present on my training data set. Whenever you are predicting, you will get one of the neurons which will have a very high value, which is close to 1. All the other neurons are going to have a value which is more or less closer to 0. And that's how we are going to define over there. So the first part is to define an initialization part. So first we will start by defining a class. So this class definition is basically trying to define your container within Python of saying that this is a particular one which I am using. So what I am going to do is that in order to define my perceptron, I define a class which is called as perceptron, and that has a data structure of the type called as a nn.module, and these nn.module is a native structure which has been called down from your torch library. So we are using torch in order to implement our PyTorch environment over here, and within torch we are going to import down my nn library. So within nn I have a particular data type which is defined as nn.module. Okay. Now within that I need to start my initialization, and this initialization is trying to say down that what is the number of inputs which goes down into my neural network over here, which is on the input side of it, and that is equal to my number of channels, which I call over here as n underscore channels. So this is exactly, if you look over here, so this n underscore channels is supposed to be equal to the length of the vector. Okay. The next part is that you need to identify what goes sort of like within the perceptron model over here, which is the starting point of my pointer on the constructor and which is my end point of the constructor. Okay. So the starting point of the constructor is what gets defined by this command of super, or which is just a superior constructor over there. So over here the first part is that I will be defining my perceptron which has this, and then my next part over there is that the perceptron is linked with itself, and this has to start its own initialization, and how it would be starting its own initialization is what is defined over here, and this keeps on giving the point that my input to it is basically a linear combination, which means that all the neurons which I have on my input side of it, they will be densely connected to all the neurons which I have on my output side. And how this is connected is that I have n number of channels in my input side, which equals to the length of the feature vector, and they connect down to all the 10 neurons on my output side over there. Now typically for this initial part there won't be much of a modification. Subsequently, when you keep on defining your network, you will have to define this part of your input to output relationship as you keep on adding subsequent more layers. So these we will be taking down into the multi-layer perceptron examples, which we take next week up while doing the theory and then subsequently to the lab. So here for our simple perceptron model, well, you have a set of inputs which are just connected down to one hot 10 cross 1 output vector. So this is what initializes and defines my perceptron model. The next part is that I need to define what is my forward pass over this model, or forward pass means that if I am giving an input, I get an output. So what is the relationship between this input to my output? Okay. Now you remember from our perceptron model over there. So my input to output relationship is that all connects which come down from my input side over there are to be connected down everything to my output, and once I have this feed forward going down, the next part is that there will be a summation which happens over there. So all the j number of neurons from my input, they will be connecting down to each of these k neurons on my output over there. Now once this summation is achieved, you always have a bias vector which is also a trainable parameter within the library itself. Then the next part is that I need to have another nonlinearity. So this nonlinearity is what gets added over here. So what this means over here is that whatever comes down as my input, that gets a linear transformation. So this linear transformation is what is already defined over here. After this linear transformation has been there, then I take this same output over here, feed it as an input to this network, and then I apply a softmax criteria over there. Now, as I have this softmax nonlinearity over there, whatever comes as my output, that is what I return from this function. So, whenever I do a call for this particular function name called as perceptron, whatever I give as input, it will have a linear transformation, then a nonlinearity of softmax imposed on top of it, and gives me my final output from there. So, this is how I define my perceptron model. So, let us run that part. So, I have my function defined over here for my neural network. So, my neural network is now just a function, and that is what how we were treating it down throughout. Now, from there, the next part which we would like to do is actually generate a data set labels accordingly. So, here if you remember, so I was telling that in this classification problem you just have a one hot vector remaining in your representation. So, in that one hot vector what comes out is that as whichever class is present over there, that particular element is going to be 1, everything else is going to be 0, but then in the labels which we had stored, so they had just numbers from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, it is not exactly a 10 cross 1 vector of which 1 is 0. So, that is what is done over here by running down another simple for loop. So, what it would do is that it would define an array of size of 50,000 and 10 columns. So, 50,000 is the number of elements in your training sample, and 10 is the number of output classes which can be present over there. And now, based on whichever is the class indicated in your train label over there, so this part, if that matches down to a particular column index on a given row, then you are just going to set that as 1, and everything else is otherwise going to remain as 0 based on this initialization given down over there. So, we can just run that part, and this generates your one hot label vectors. Now, once that is done, the next part is that you can actually create a PyTorch data set from your feature matrix. And now where this comes down from the fact is that your earlier data structures and whatever variables you are using, so they were all in NumPy format, and NumPy is a library which so all NumPy format libraries are used within NumPy constructor itself. So, whenever you are dealing with Torch as another library, it has its own data type definitions to go there. So, you need some sort of a wrapper in order to wrap anything, any variable which is given as a NumPy constructor onto a Torch equivalent constructor, and for that the functions which are needed are something which is called as a Torch from NumPy. So, what this effectively does is that given any array in NumPy, you are going to convert it into a Torch equivalent one and then pack it down into a tensor data set itself. So, these are all Torch tensors which get created. So, we need to create that for the training and testing for both of them. So, just running this one creates it for the training and testing, and then after that for the sake of the library and how it works out is that you also have something called as a data loader. So, this data loader's main efficiency is that when you are trying to load data onto say a GPU device over there, so you have a lot of memory transfers going down between your RAM to the GPU. Now, if you remember from your other related classes on computer organization, so remember that these do happen down in fetch cycles over there. Now, these fetch cycles would typically be when I fetch down some part of my memory from my RAM onto from my CPU RAM or system RAM onto my GPU RAM, and then in the GPU the rest of the code keeps on working. Now, while this code keeps on running in the GPU, my CPU is not doing anything and I am not even making use of the CPU RAM. So, I can now prefetch the next set of data which will be needed for operating on the GPU in this duration, and that will actually pipeline and speed up my whole operation instead of having to wait for the GPU operation to get over and then write it back to the RAM and then fetch the next one. So, this data loader is basically is a wise function which has been provided within the library, which can fetch down 64 such units of samples from your CPU RAM onto the GPU RAM at any given point of time. And in fact, this does also work down within while you are even trying to fetch down from your hard drive onto your RAM as well. So, we will be covering that into as we go into much more detailed classes as well. So, as of now, this data loader is now made down to optimize and then fetch down it prefetch everything before it keeps on working. Now, the next part which we are going to look at is actually check down whether GPU is available on the system. In case a GPU is not available, then we do not use a GPU. So, the typecasting and everything, nothing is going to get done. So, your GPU, in order for it to work on the data, so the data has to reside on the RAM present in the GPU. you cannot directly operate on the RAM which is present on the CPU. They are on two different data buses over there. So you will fetch, and that fetch happens through your data loader. Once you have fetched over there, then within your GPU memory itself, you can keep on operating everything. So if this is not there, then, but the point is, whenever you are fetching and putting it onto GPU, it means that there is another kind of a typecasting which goes on. So if the device is not found, then we will not be doing that typecasting, because the rest of the codes on CPU, they cannot make use of the GPU typecaster itself. So here my typecasting gets over, and then I start by defining the function for training the network. So once you had your network defined, the next part is that you need to define the trainer. So this trainer is basically a part where you are defining your forward pass, which means that given an x, you get an output y. Okay. Now what you are getting down was a y hat, which was a predicted part of y. You have your original y, which is the ground truth available. Now based on that, you are going to calculate a difference between them, which is your cost function. So we had used the MSE or L2 norm as a cost function over there in order to find out our JW, which was the cost associated with the weights. So this part of the algebra which gets transformed onto a code is what comes down within your training routine. So as a simple part, what we define is training model function over here. So the input to this one is a pointer, which is the model or the neural network given down over there. Next is the criteria, which is basically the cost function which I am going to use, that is also referred to within these libraries as criterion function. The number of epochs over which it is going to learn. So number of epochs basically is the number of iterations over which I would do. So remember from my last theory class explanation that you start with some arbitrary value, you put your input data, you get some predicted output y hat, you take a difference between them, so that is your cost. Now based on that cost, you will be taking a derivative of the cost and then back propagating it over the weights back. Now once you have done this one, this is over the first epoch. Then with these revised weights, you are again going to put down your input x over there and get down another predicted value y hat, get down a new value of JW, which is at the end of the second epoch, and then again back propagate, and this keeps on going. So that is what is called as epoch, these iteration counter over there. The next part is learning rate, which is your eta factor which comes down into your weight update rule. So your W new was W of n plus 1 was equal to W of n minus eta times del W of JW. So this eta factor over there was my learning rate, which was helping me scale down and put down this gradient in the order of the magnitude of the weights itself, so that they can all scale down in a similar way and there are no erratic variations. So what we start initially is we put down a pointer which is called as a starting time pointer. Then so this is just to show you how much long it takes to traverse down per epoch. Then we create a few lists. So one of them is for the training loss, one is for training accuracy, another is just for accumulating out temporary labels or whatever is the prediction which comes down at the end of per epoch. Now we start down by running a counter which runs over the number of epochs over here. So epoch is my loop counter variable over here, and then this exists in the range of 1 to the number of epochs. Okay. So it is basically equal to the counter goes up to the total number of epochs which is present over there. So let us define a small timer variable over here, which is my epochs start time. Now this is just a small printer for printing down like how many epochs out of how many epochs have elapsed out as of now. And then so running loss is a loss is basically the criterion of the cost function evaluated within that particular epoch, and that is zeroed down at the start of every epoch and keeps on accumulating as we keep on going across the epoch. Now the point is that we will start with loading data. So my initial data loader will go down into a batch size of 0 or the minimum batch size which it takes. So then so what this definitely means is that I will load, so I will basically traverse one data point at a time and go through it. Okay. So within my data over here which exists in my train loader. So here what we are basically defining is that another loop on which we are looking at the total number of data points existing. So if I have 50,000 ones, so within each epoch for every single sample I am going to do a feed forward, then find its error, and then I will be back propagating it over there. So this is per sample based over there. So going from there, you remember that we had done this flag of use GPU. So if this is set to true, that means that a GPU exists, and whenever there is a GPU existing, we need to typecast the variable and set it as CUDA. So if the GPU does not exist, then anyways it comes down as else over here, and then I don't need to typecast any of these. Now the way of converting and writing inputs as variable inputs is of the fact that this particular library of PyTorch is based on a dynamic graph build up constructor, and there they have a separate data type which is called as a variable, and if you are not defining certain thing as an explicit variable within the library, so they will be taken as constants across, and there will be no modifications over there. So we in order so that these can be used within your update rules, we are putting them into another typecaster which is called as variable, and this is pretty much intrinsic to the library itself, that there is no algebraic restriction as to why you need to do that. This is from reasoning best left down to the library builders itself. Now from there, the first thing which you need to do is, you remember that we had a del w of jw to be calculated, and this value has to be set down initially to 0, and that's what we do with the 0 grad factor over there. Now once that is done, I will get my set of outputs. So this set of outputs is basically if model is, which is my function, which is that neural network which I had created. So whatever is my input I put down to that model, I get a set of outputs, and that output is what is the output of the network which I get. Now once I have this output of the network coming down over there, then what I would like to find out is basically that which particular class over there has the maximum probability of occurring. Okay. So once I get that whichever class has the maximum probability of occurring, so I will be just be putting that particular class as a 1 hot, everything else is going to subside down towards 0. Now once that is placed down into my prediction, so these are basically predictions of whichever is the maximum probability of that coming down. Next I define down my criteria function as the so this is my loss, and that loss is defined in terms of my criteria function. Now here the input to my loss function or my jw is basically y hat and y. Okay. So y hat is my predicted output which is given over here, and y is the exact ground truth label which is supposed to be present, and that's my labels over here. Now once that is done, I can start accumulating my losses within every single epoch. So in an epoch it will take all the samples and then keep on calculating losses for each sample, and then we will add down losses for each sample together itself. So and that would give me the total loss at the end of passing down all the samples through an epoch. Now once I have that part done, then I can actually find out what is my total loss in that complete epoch, and that is what is found out over here. So I take my running loss, and from there I get my so basically I get my running loss over here, and I have the loss given down from one particular data, and then when I start my back propagating over there, first is find out what is my total loss or the total error which occurs over there, and then I can divide it with the batch size which is equal to basically the total number of samples which were given down in one particular epoch. Now batching concepts we will come down a bit later on. It may so happen that you might not need to push down all the 50,000 data points into one single epoch in one single shot and calculate for each of them, but you can push it down into say 100 samples out of this 50,000 go in together, their error is calculated and that is back propagated, and next you have another 100. So it would mean that there can be multiple back propagations within the same epoch as well, whereas here we are looking into one single back propagation which can happen. Now whenever we write down this total loss dot backward, that is the derivative of my loss function which is calculated. So my del w of jw, in order for this to be calculated, I need a like basically j first derivative of my cost function, if you remember. So that first derivative of my cost function is what is also called as a backward operator over here. Now once that is done, the next part is that I need to get down my network parameters and keep on updating my network parameters as well. So in my network parameters, I write down another loop over here which will basically be counting down all my model parameters. So model parameters is the function which gives me all the free parameters in a model, or basically all the weights which are present within my neural network which can be updated. So within your neural network, the only thing which can be updated are basically the weights. You cannot update anything related to the you cannot update anything which is related to the this nonlinearity present over there in any way. So, since you do not have any updation to be done with the nonlinearity, so the only trainable parameter left down for you is just the weights. Now, what we need to get is, once you get down pointers to each of these weights coming down, next is you need to find out what is your so we have calculated our training loss and everything going down over there. This is just a small script to print that at any given point of time. The next is that you will have to basically update each of them. So, for updating, you will be running down through the rest of it, and then as you keep on going, so what we definitely find out over here is that there is so you have your feed forward happening down, and then you get your error calculated. From there you will be getting your gradients calculated. You have the gradient for the loss function, you have your gradient for the network, everything done. With these you can now update all of your weights, which goes within your update routine over there. Once the update is over, the next part which remains for us is just to keep on looking into the errors. Okay, so initially we will start with a very naive approach of just trying to look into the errors and see whether the error is coming down and maybe just plot it down. But as we keep on going, I will be coming down to a point for very deeper networks where you take on for a longer duration of time as to what are strategies, and then how do you come down with some way where just by looking into errors you can come down to a point where you can just converge and stop and not take them any further. So, let us just run it down. So, what I have done is, so this is the function which gets defined, and once that is done, we need to start with the training. Now, in the training part over there, so this is your train model function which we had defined over here. So, now, so that the whole complex procedure is now just a function call for me. So, over here I need to put down my model, which comes down from my perceptron, which is defined over here, that exists on my CUDA because I have a GPU running with me. Then I have my criterion, which is defined over here, which is my MSE loss or mean square error loss. The number of epochs I am using this is for 20 epochs, and the learning rate over here is kept at 10. And so this has been empirically optimized. You can definitely play around with 100 or 10 power minus 3 and just check around. You will find like real fun around over there. So, just let us run this part. So, you can see these epochs going down. So 0 out of 19, which means the 0th epoch which has run down. So, this barely takes down about a second, and if you look into these errors over there, so somewhere around this point is where the error is changing. So, it is changing at a much slower rate, really slow and tardy rate, but you see you can clearly see that these errors do keep on changing. And so, going at the rate of 1 second, it's somewhere around 20 seconds that so the total thing takes maximum of 27 seconds in which, and this is how the rate is going down. Now, clearly going down by this, I do know that this will keep on continuing further and go down. So, please keep on putting your errors as towards a large number of epochs. Now, this is the other side of it where we are looking into the accuracy plot, and if you clearly see, as the error is decreasing, your accuracy is definitely increasing over there, but then this accuracy is not that high. So, it is just at barely 12.5% on your accuracy side over there. So, once that is done, that is on your training part of it. The next part is to look down into your accuracy over your test set. Unfortunately, with although it had a 12.5% accuracy on the training set, on the test set it just unfortunately came down as 0. So, if you keep on running this for a longer time, so we know that from our experiences, if we were training this for say about 200 epochs or so, you do come down to a point where you can have about 10-12% of accuracy very easily coming down. So, I will leave these exercises more of to you to explore and have fun along with that. And with then next week we will be continuing with multi-layer perceptrons and having much more exercises into understanding multi-layer perceptrons as well. So, with that stay tuned and thanks.